Okay, so welcome to today's webinar. Today we have Andriy Norets from Brown University in the US. So he's worked extensively on the application of Bayesian non-parametrics in econometrics, particularly around asymptotic results and computational kind of strategies. So today he's going to be talking about estimation of dynamic discrete choice models. I'll hand over to you, Andriy.
Thank you for the invitation to present to the organizers, and thank you all for coming, attending the webinar. This is joint work with Kenichi Shimizu. And in this paper, we are bringing Bayesian non-parametric tools, mixture models, into estimation of a particular class of economic models called dynamic discrete choice models, sometimes also called structural models. So what does that structural refer to is that we are actually explicitly modeling economic behavioral agents. And we sort of think that the agents maximize the expected utility. And it is a dynamic model. So we have some state variables that evolve over time. Every time period, agents make a choice out of finite set of possible alternatives. And given that choice and state variables, they get per period utility, denoted by U. The choice affects the utility, but also it affects the evolution of the state variables and hence future utilities. And that's why it is a dynamic model. In this model, the agents have some shocks, denoted by epsilon, and we need it in sort of model that can be estimated, right? They also have some observed state variables. They are observed by the statistician or econometrician and also the agent. We also have time discounting with some factor beta, and utility functions depend on parameters theta, and also transition probabilities for the observed state variables depend on the parameter that we are estimating here. And the main objective when we estimate this type of models is to actually use these models for some kind of policy experiments, counterfactual policy experiments. Why are we doing that? Because in many situations, it would be very expensive to actually conduct some kind of experiments and get data on what would happen if we change some policy variables. Let's say if we are changing copays in insurance policy, it is very expensive and would be unethical to conduct this type of experiments. And this model would be kind of like a laboratory where we would run this type of experiments that we actually have not performed. And from the model, we get some kind of predictions that we can use at some early stages of the policy analysis. So this type of experiment is called counterfactual experiments. So this model has a recursive structure. So at any point in time, it looks like we are exactly at the initial state, but with different value of state variables. So that's why it can be rewritten recursively in this form of so-called Bellman equation. So we have expected value of choosing alternative dt. It's given by utility plus discounted expected value of the future utilities, given that the agent will optimally make choices in the future as well. Okay, so the way to solve this type of models is we can use a so-called value function iteration. Basically, we can iterate on the Bellman equation, starting with some arbitrary guess for function v. So this equation is contraction mapping, so there is a unique solution, and we are guaranteed to converge to it if we do that. Of course, when x is finite, it's just a kind of a system of a nonlinear equation with finite number of unknowns, and we can try to solve it using maybe Newton method or something like that as well. Or we can combine value function iteration and Newton method. So if we have parameter value, for a given parameter value, we can actually obtain this solution to the Bellman equation, and we basically have then an optimal choice. So we'll just choose the alternative that gives us the largest value of v x d dt plus epsilon dt. Okay. So examples of the applications that we actually going to be looking at in our paper would be one where a patient makes decision when they get a particular type of disease. They make a decision about whether they want to visit a doctor or not, and whether they're going to take leave of absence, sick leave or not. And so the state variables would be how many doctor visits and work absences they already accumulated. And utility will depend on things like patients would have to pay copay to visit a doctor, and they would have to forego some portion of their income when they use sick days, things like that. And then the counterfactual experiment would actually be, what if we change the copay? How much more patients would use doctors? Okay. So when we estimate these models, we usually have panel data where we observe these observed state variables and the agent's choices. The likelihood function will have this simple form where we have this so-called conditional choice probability. So we see a choice, and conditional on the state variables, it's simply going to be the probability that value v of this optimal alternative plus the corresponding epsilon shock is greater than value and this epsilon shocks for all other alternatives. Okay, and to compute the value function, of course, we would need to solve the Bellman equation to obtain this v, and we would have to integrate out epsilon in the conditional choice probability, and also we would have to compute these integrals of epsilons in the Bellman equation solution. Right, there is this so-called Emax function, so we have expectation over max of these v's plus epsilons, and if dimension is more than 1, 2, 3, it could become quite hard to integrate these epsilons precisely numerically. So this type of models are widely used in different subfields of economics, occupational choice, job search, some kind of firm entry exits decisions. And these models are pretty challenging computationally, right? We need to solve these dynamic programs to compute the value function and integrate out those epsilons in the Bellman equation and in the likelihood. And people came up with some simplifying parametric assumptions on the epsilon, distributional assumptions. Specifically, if you use extreme value type 1 or Gumbel, same thing, distribution for these utility shocks, then we can integrate these shocks analytically from the in the likelihood function. It's going to be just this kind of logistic like multinomial logic like probabilities, exponent of the value, deterministic part of the value divided by the sum of the exponents. I'll show you some equations later on, but roughly you get an idea. And same thing goes for this Emax function in the Bellman equation. If we assume extreme value IID, then we can obtain actually analytical expressions for these Emax integrals over epsilons. And so that's fine. Of course, people use exactly that in most of the application of this type of models. And yet it is, of course, desirable, if possible, if feasible, to relax the distributional assumptions and see if the counterfactuals, estimation results are sensitive to the distributional assumptions on the epsilons. Because epsilons are unobservable, so it's kind of hard to make good assumptions on them. So it's better to treat them non-parametrically, which we will do in this video. There is some literature on non-parametric treatment of epsilons, and it mostly involves something like epsilons, sort of like measurement errors, and we have some good information about measurement, some additional variables that kind of let us identify the epsilons. So that could be unrealistic in many settings, and people sort of figured out how not to make assumptions on epsilons in binary choice. But in multinomial general case, there are no feasible estimation strategies for non-parametric treatment of epsilons in this model. So here we come. We're gonna use location scale mixtures of extreme values, and there are two obvious benefits. So first of all, since we are using the mixtures of these extreme values, all these analytical expressions for the choice probabilities and Emaxes, they will also have this kind of mixture forms of familiar expressions for the logic model. So the model is still going to be computationally tractable. And at the same time, we also know that location scale mixtures can approximate quite large classes of densities. Of course, it will depend exactly on which norm we are using, and some assumptions need to be made. But potentially, at least we know from the literature on norm mixture of normals that they basically deliver optimal approximations in many different settings, multivariate, conditional, and for some kind of discrete continuous distributions as well. So that motivates our use of location scale mixture models. So here is the outline. I will talk a little bit more about this dynamic logic model and what happens when we use mixtures. Then I will talk about approximation results in the context of this model, because we have to use a particular type of distances that would bring model solutions. So it can approximate model solutions as well, not just some kind of arbitrary metric approximation results. And then I'll also have some discussion of some of the asymptotic results that we can get, and maybe I will discuss some of the challenges that are still sort of remain for at least sort of theoretical asymptotic analysis of the approach we propose here. I'll also discuss a couple of applications. One of them I already mentioned, a model of medical care use and work absences, and also a very simple model for which we can actually compute identified sets for the parameters, and then we can compare IMCMC results with that. That is actually true exact results. Okay, so that's the plan. And let me get right into it. So here is this extreme value type 1 distribution, or Gumbel distribution for shocks. So we're gonna add this location and scale, but it doesn't change this analytical convenient analytical properties of the extreme value. So then this conditional choice probabilities, so basically the probability that the value of x Vxd plus epsilon is greater than of the same values for other values of the alternative or the choice. And that's going to have this nice logistic multinomial logic-like form. So it's going to be exponent of, well, we have location mu j plus the value, and it's divided by sigma, and then it's normalized by the sum of these things for all other alternatives. So that's exactly how we would get multinomial logic, right? And similarly for this Emax, the expectation of the max of values that we have in this Bellman equation that we would need to actually compute when we do the dynamic programming solution. So that also has a very nice analytical form. So it's a log of sum of the exponents, and these functions are infinitely smooth, so they're differentiable, so we can lean on computing the derivatives for these models, and things going to be simplified greatly when we do something like that. So that's just the standard dynamic logic introduced by John Russ, so kind of just extension of static multinomial logic to dynamic case. Now, when we use mixture models, it's convenient to represent mixtures as first we draw this allocation variable S, and conditional on the allocation variable, our epsilon is just coming from extreme value distribution with corresponding location mu sj and scale sigma sj. And so, of course, equivalently, it's just a mixture model for the epsilon, right? Just one way to write it. But when we condition on x, explicitly, it becomes clear that all sorts of expectation, when we take with respect to mixture models, will just be like mixtures of expectations, right? And so given that, the conditional choice probabilities will now be just mixtures of this multinomial logic-like probabilities. And similarly for the Emax function, it's just going to be a mixture of these Emaxes for the dynamic logic case. So here, I went over the model quickly, but it's so it's just like imagine a standard multinomial choice model, like a multinomial probit. So it's clear that if we model epsilons non-parametrically, then there is no restriction in fixing epsilon for one of the base alternatives. And let's call it 0 alternative, just fixing the epsilons to 0, right? Because the choice depends only on the difference between epsilons. And so hence, because we are comparing value of alternative 1 plus epsilon 1 to value of alternative 2 plus epsilon 2. So it always depends on basically some kind of delta epsilons. And so hence we can just renormalize and fix one of the epsilons to 0. And it turns out that if you still preserve this sort of location scale of extreme values, or just use extreme values as one of the epsilons fixed to 0, you still get analytical expression. They will be a little bit uglier than this nice exponent divided by sum of exponent and log of sum of exponent, but still they are represented in terms of known functions with known derivatives that MATLAB can compute the functions and derivatives as well. So actually we do this normalization to reduce the dimension, because here we can just reduce dimension by 1 in modeling non-parametrically the distribution of this vector of epsilons. And so that's what we do. I'm not showing these ugly expressions. They're in the paper. If people are interested, they can look it up in an appendix. Okay. So how do we do estimation? So there is no conjugacy here whatsoever, right? Because we have these Bellman equations or values that need to be obtained numerically, right? And they are nonlinear functions of some functions of parameters that we can evaluate by solving the dynamic program, but we don't have functional form for them or anything like that. At the same time, because we are using these dynamic logic-like things, the Bellman equations, after we integrate out epsilons, they look like system of nonlinear equations where we can actually compute derivatives using implicit function theorem, so derivatives of v, and that means that the likelihood function, which is a function of this functions v's, so it will also be differentiable. And so hence we can rely on this Hamiltonian Monte Carlo methods that that would need derivatives. Unfortunately, we cannot use something like Stan because we have to solve the dynamic program. So we have to, we ended up using MATLAB HMC package for performing this Hamiltonian Monte Carlo update conditional on fixed number of mixture components. For doing inference on number of mixture components, we're really trying to make the model non-parametric here. So we will have a prior on the number of mixture components, and we will use a reversible jump algorithm from my paper from a couple of years ago. So the idea here is quite intuitive. I just provide a bit more precise optimality results for why this is a good idea. So what we are doing, we are constraining ourselves to adding or deleting one mixture component at a time. Okay, And we have to represent the model as if we can just add the parameters to the vector of parameters. So we have this phi j is basically the mixing weight, location, and scale. And mixing weight has to make sense for arbitrary number of mixture components. So hence we use unnormalized mixing weights. And in these settings, it turns out it is optimal. And optimality here is in the following sense. First of all, some expected acceptance probabilities for drawing M are maximized. And moreover, using Pescun results, I show that at least under some kind of constraints on, ordering of blocks in the MCMC to make the Markov chain reversible, and anyway, there are some restrictions on that. But what you get is that the functions of the number of mixture components estimated from this type of MCMC run will have the smallest possible variance. So it's kind of, we rely on results from Pescun and Tierney's generalization to arbitrary state spaces for Markov chains, and using the so-called Pescun orderings to show that it's optimal. And so it actually works pretty well. I used this before in some other context, and for mixtures of experts, for example, when I try to add this additional experts or mixture components in models with where mixing weights depend on covariates, and that's where sort of I came up with the idea, and it turned out to work well. And even in simple mixtures, I actually check in settings similar to some kind of Dirichlet process mixture type of settings. This reversible jump works actually better than this alternatives based on Gibbs sampling proposed by Neil and some other people. So I would encourage everyone to take a look at it and try it out. So reversible jump actually does work reasonably well, at least in these settings. Okay, so what is exactly this optimal? So the proposal will actually be so when we are adding a new component, m+1, the proposal will actually be a conditional posterior for parameters of component m+1, given the number of components is m+1, but we keep first m component parameters of those fixed. Okay, and so it has some nice, so we can compute it up to normalization constants. So it's going to be just the likelihood function conditional on m+1 times the prior distribution. Actually, to compute the Metropolis Hastings acceptance probability for the reversible jump, we need the normalization constant. And that's why we use approximation to this conditional posterior for the component m+1, the computing the posterior mode using Newton method. Again, everything is differentiable here. And then we use minus Hessian as the variance and use normal distribution, where we can, of course, compute all the normalization constant in actual implementation. So this is roughly how, in broad terms, the MCMC algorithm in this model works. And I'll show you some simulation results later on when we get to applications. So let me briefly mention the theoretical result that we are deriving in this paper. So first, we need to figure out what would be an appropriate metric on the distribution, so that this basically likelihood function, the CCP, conditional choice probabilities, and the solution to the Bellman equation as a first step before we show the results for CCP, so that we get continuity, so that if we are approximating distributions by mixtures in this metric, we also get approximation for the conditional choice probabilities and solution to the dynamic problem. And I will also talk a little bit about asymptotics. posterior consistency for the identified sets, and maybe how to do frequentist inference if you really want to, using the MCMC output that our method would produce. So first of all, so this continuity result, so the distance on the distribution that we need to use here is something like a total variation distance, but also we add kind of like a first moment. So we have this absolute value of epsilon j in the distance rho for two distributions. And the distance kind of makes sense if you look at the dynamic program formulation. These epsilons enter additively, right? And we have like a max over epsilons plus something. And so how can we make these maxes close to each other? And then it's clear that we would need to make the integrals of, like, say, some kind of functions of linear functions of epsilon, or at least piecewise linear functions of epsilon, to get close to, right? And of course, we also will compute some kind of constants times integrals over epsilons, and so we need total variation as well. And I don't think that we can go weaker than that. So that's our distance. Okay, and it turns out that so this Emax function and correspondingly then conditional choice probability is going to be continuous under some regularity condition in distributions using this distance on F1 and on the densities for epsilons. So we so here we just use the very maybe somewhat stronger than necessary conditions for the class of densities that can be approximated but by mixtures of extreme value IID distributions. So we have this kind of Lipschitz type of condition with some envelope function that has to satisfy some conditions. Of course, generally, I think since it's you probably don't need it, but proofs are very short and nice, so we just decided to keep it short at this point. But these are the conditions on the class of densities that we can approximate by mixtures of extreme values here in this distance rho. There is also an alternative to these approximation results, and it's somewhat, I'm not sure if it's really a positive or negative development for this type of models, but anyway, what we also know that if X, basically this state variable, if it can take only finite number of values, then this dynamic program becomes basically these V's functions become just vectors, and the way distribution of epsilons enter this model is pretty much only through some kind of integrals of epsilons over some subsets, different subsets. So basically only finite number of characteristics of F will determine the solution to the dynamic program. And hence, you know, mixtures are pretty flexible, have lots of parameters. So it turns out that not only they can approximate with some arbitrarily small error the distribution of epsilons, but they can also approximate exactly this finite number of characteristics of the distribution that are essential for the dynamic program solution, and they can match them exactly. So start with some arbitrary F0 distribution of epsilons, and we can find a finite mixture Fm that's going to match, that's going to result in exact match of this Emax function and the conditional choice probabilities. So we have these two types of approximation results, if you will, at least for finite X. This can also work to get the following implication of the Schwartz posterior consistency theorem. So we make some bunch of regularity conditions so that this dynamic program has a solution, things are bounded, And moreover, to make things simple, we assume that X belongs to a finite set, so there's a finite number of the state variable values. Then basically, in this case, the choice probabilities become just not functions, but collections of vectors. So we have just finite number of objects, and they are like they live on simplexes. And for these basically discrete distributions, all these metrics, weak, strong, right? Or Kullback-Leibler, they are all equivalent. And so hence it's really straightforward to apply Schwarz posterior consistency theorem. All we have to show is that our prior puts enough mass around theta naught and also around f naught, and we have this approximation results and continuity. So it's really kind of just a straightforward implication. Then Schwarz posterior consistency theorem implies that in weak topology, we have this consistency, but weak topology here is basically equivalent to anything else. And so hence we can easily conclude that we will not put any posterior probability in the limit that will give us these conditional choice probabilities that are different by more than some arbitrary small number delta from the true conditional choice probabilities. So that's kind of nice that we at least not going to put weight on the wrong parameter values or outside of arbitrarily small ball around true parameter. But at the same time, it's not completely clear from this result, or not clear at all actually, how the posterior probability is going to spread inside this on theta and f that give us choice probability p of theta and f that is close to p of theta naught f naught. And intuition suggests, of course, that it should basically be a posterior should basically converge to a conditional prior. So let me give you a little bit more explanation on that. So we have a prior on theta and f, right? This mixture model for f, and theta is a parameter of utility, so it's a finite dimensional vector. So we just have some kind of normal or mixture of normals type of priors to be flexible. And that induces a prior distribution on the so-called reduced form parameter choice probabilities. And likelihood function depends on theta and f only through p. So we can, in a way, sort of think about p as a parameter, if we want to do inference on p. And the map from theta f into p and prior on theta and f, basically this thing define a joint prior distribution, if you will, on theta f and p. And we can assume, so we cannot prove it. It's kind of I'm not sure what the techniques are appropriate here. If you have some ideas, let me know. But in similar settings, not for these models, but overall, kind of in set identified settings, people made assumptions that this sort of conditional distribution or conditional prior of theta f given p is just in general could be reduced form parameters, and theta f are these structural parameters in the model that could be set identified like it is here. So people assume that it's this conditional prior is continuous in p in suitable metric, and then if that is the case, then your posterior for p clearly converges to p naught, kind of like, for example, implied by Schwarz posterior consistency theorem that we just saw. And then your posterior on theta and f then should naturally be converging to this conditional prior, conditional on true value of p naught. So basically, that's how posterior should spread the weight on the identified set. And so that's roughly what we can say, but sort of establishing this continuity turned out to be a bit too difficult, at least at this point. So we keep it as a kind of conjecture. So under this assumption, that's what we would get, and it kind of makes sense. Okay. So now let me briefly describe how we could do frequentist inference based on MCMC output here. So what we're gonna do here, so let's start through sort of a Bayesian justification for what could be done. So here the likelihood function depends on theta and f only through this what can be called or sometimes called reduced form parameter p, choice probabilities. Okay, and in choice probabilities, the likelihood function looks just like a nice multinomial likelihood. So as long as prior on p is nice, which we show at least it can put mass around true values for at least some class of f naughts. So then presumably the posterior for p, not for theta and f, but for p for reduced form parameter, will have some kind of form of Bernstein-von Mises theorem, right? Because likelihood is simple, nice. It's a parametric problem. Then what we're going to do, we're going to try to do inference on theta and f with uncertainty that's sort of implied only by uncertainty about p. And so specifically, let's introduce notation, the identified set on some kind of function of theta and f. It could be just theta, some components of theta, for example, or it could be this counterfactual, like what happens to number of doctor visits or something like that. So all these values consistent with p, so that the theta and f give us that exact p, will be called identified set for this parameter eta. And then what we're gonna do, if we want to have a set estimator for this eta, we're gonna look at the union of these identified sets, and we're gonna vary p over basically a credible set, 1 minus alpha credible set on p. And of course, if Bernstein-von Mises theorem holds, then the set b 1 minus alpha p will have coverage for p, right, by Bernstein-von Mises theorem. But then, of course, this union of sets will have a coverage for the true identified set just by construction, right? It's just the union it will cover. And so then when we get our MCMC, we will have draws of theta, f, and p. And then we're going to construct standard credible set based on normal approximation. So we'll compute the mean for p and variance covariance function, and asymptotically. So we have the critical value chi-squared 1 minus alpha times the number of parameters in p, or number of components in p. So we just basically use normal approximation to construct a credible and confidence set on the reduced form parameter p, and then we just take all the values of theta and f that result in p that's in this credible confidence set, and so that's going to be our approximation for this sort of union of for the credible set for the identified set on eta. Okay, so now let me quickly get into rough description of the application. So first application is like the simplest possible dynamic discrete choice models. Rust uses it to introduce this dynamic logic model, and everyone who introduces a new method for dynamic discrete choice models uses this setup. So it's a model of bus engine replacement. We have some kind of costs of maintaining engine that depends on mileage x, and when we replace the engine, we pay theta naught, and so then utility functions can be written as a linear function of the mileage, and the difference in extreme values is a logistic. So we just put this logistic epsilon in one of these alternatives. The mileage evolves, basically mileage for the bus is discretized, and it can only jump into over basically 2 mileage ranges, and we would estimate this pi naught, pi 1, pi 2 from the data, and then we'll try to estimate theta naught, theta 1 using this method that we just discussed. So in this simple model, this is how the identified set, when we treat distribution of epsilons as unknown, so the red dot is a value of parameters that we use to generate this, to solve the model, right? But then when we don't make the distributional assumption on epsilons, so all these other values inside this set are consistent with the model solution and some distribution of epsilon. Okay, so that's what we call identified set. So all these thetas with F give us actually P that we obtain from solving the model for these red dot parameter values. And so now we can compute this identified set. So now we want to see if our MCMC procedure, estimation procedure recovers that. And so the more data we have, roughly these are the draws that we get, and this together with the identified set. And as we get more data, we get more and more sort of alignment. It's not perfect. There are some corners. I suspect those are like a very weird distribution. So to obtain this identified set, we have to solve linear programs, and on the edges they are almost like ill-conditioned and whatnot. It might. So I'm not quite sure about really the corners here, but overall we get a pretty good idea about the identified set here. And this is showing that it's not just we get one draw, but it's kind of a 3D. So these are iterations, and this is identified set at the bottom, and these are the draws as Markov chain goes. So we see that we keep coming back again and again. So this is how this reversible jump on number of mixture components works. So you see it looks like pretty stable. So we have here like 50,000 iterations. So the draws for M looks pretty stationary. So we see that actually not a large number of draws is sufficient. So we kind of, one is not enough, but two has the highest posterior probability given the prior. And this kind of label invariant object that also look pretty stationary here. All right, now let me get into actually a little bit more substantive application where we actually look at some counterfactuals. I think I don't have really time to explain the model in too much of details, but here basically we have four alternatives: work, no treatment; work and treatment; no work, no treatment; no work, treatment. And the state variables is number of days since the beginning of the illness, and then accumulated number of doctor visits and work absences. And then utility will depend on, we are exhausting the number of sick days we have, and there is some kind of calibrated function of how our income changes as we use more and more sick days. And for doctor visits, we have to pay, and we might dislike it, spending time on it. So it's all kind of in the utility functions. So the original paper was actually very nice. It got this award for the best paper in Econometrica in 2 years in 1998. And so we use it to illustrate how different the estimation results would look like if we use our technology for estimating this model. And so let me jump to actual results. So this is, we are looking at expected number of doctor visits. And this is from just the estimated model. So it's not counterfactual, it's kind of actual number of expected doctor visits. And here we present the posterior distribution, and it has like this heavy kind of tail. So we do have these draws that goes all the way up, like in the tails up to 5 and like closer to 0. And then we construct a bunch of set estimators. So we have, of course, the standard HPD set. Then we have set that's based on MLE and assuming this dynamic logic model, kind of what would be in the original paper. And we also report this credible set for the identified sets. And it's like this biggest set in the picture. So it's white. So for the actual environment, and the data where from, so for the actual environment, you see that all the intervals include the true value because we are doing it for artificial data, so we know what the true value is implied by the model for the expected number of doctor visits. But then we also do a counterfactual, where we the same counterfactual that was done in Zhilevsky, the original paper, where they change the copay to zero, basically universal healthcare counterfactual. And so here we see that there is a large shift in the true value of doctor visits, and posterior, of course, is still kind of narrow, and the HPD set misses the true value by just a little bit, and this credible set for the identified set that presumably should have coverage, at least in large samples, is actually pretty wide, but it does include the counterfactual. So the message here, of course, the ideal situation is just you carefully look at the posterior and you treat seriously what happens in details. Because here the prior, like how this mixture priors inside this dynamic program, what exactly they imply for this object of interest is sort of hard to judge. And in a sense, this the whole posterior, even points that are not that very likely on the posterior, should be carefully considered. And at the same time, if you want a set estimator, then maybe going with this credible set for the identified sets might be a reasonable thing to consider, because it's kind of should sort of annihilate the effect of the prior on theta and f, because it operates only through P, which is exactly identified and for which Bernstein-Lamides theorem presumably applies. And so using only that uncertainty and sort of trying to get rid of the prior on theta and f would give this kind of set estimator. And so maybe it makes sense to treat it seriously here as well. So let me conclude. We propose a tractable estimation method for multinomial dynamic discrete choice models, where we treat distribution of epsilons non-parametrically. We have some theoretical results for approximation results and posterior consistency. In applications, we see that it can make quite a difference, especially when we are looking at assessing the counterfactual results. And this is exactly what's important in these models. More generally, it seems like using mixture models, and in this case, this extreme value distribution mixture seems quite promising in making these economic structural models arbitrarily flexible and yet still tractable for estimation. Okay, that's it.
So, thank you, Andriy. So there was one, I think, a question in the chat. So maybe we can deal with that from Elena Goldman. So if you've got the chat there. So the question is, I was just wondering if the derivatives are continuous functions, how would you do HMC with discontinuous gradients?
Yeah, I'm not sure how you would do it with discontinuous gradients, but in this case, derivatives are continuous. So we don't have to worry about that. Derivatives are actually quite nice. I mean, but in a way, to prove differentiability, you use a implicit function theorem on general Banach spaces, and so in general, like derivatives will be, by definition, they exist if they are kind of continuous, right? So we have a result, maybe not in this paper specifically, but I actually have a paper on differentiability, and I think John Rust in his original papers looked specifically at these specific dynamic logic settings and proved differentiability with respect to parameters of this value function and correspondingly choice probabilities.
Okay, so I'm going to throw things open. So does anyone have any questions? So put your hand up, or you can unmute and ask a question. Okay, so I had a question. So you have this mixture of gumballs, that's right. So I mean, if you were to do something else, mixture of normals or something, I mean, how important is the kernel in your theoretical results?
For the theoretical results, kernel is actually not important, and the way we formulate the result is the kernel has to satisfy some conditions that extreme value distribution satisfies. So for theory, yeah, our result is kind of for a class of kernels. At the same time, for actual tractability, extreme values are essential because they give us this analytical expression for the choice probabilities and for the integrals of the inside the Bellman equations. And so that's the main reason for using them.
Okay, thank you. So I think Elena's come back. So feel free to. Okay, so I think she was thinking about a different kind of model in terms of her question before. Okay, so are there any other questions? Okay, so if not, then I'm going to bring things to a close. So thanks for the interesting talk, Andriy, and we'll be back in January with a talk from Cecilia Ballocci.